Okay, in part 2 of this gas law chapter, I want to introduce the ideal gas law. Now, if we were in class, I'd have you shout out or say some of the things you notice that are different between the ideal gas law and the previous gas laws in part 1, like Charles' law, Boyle's law, Gay-Lussac's law. And hopefully what you'd come up with is one, you'd notice there's this R here. And R is a gas constant. And it's so a constant means it's always going to have the same value. And the value I'm going to give you is 0.021 liters times atmospheres moles per Kelvin. Now you could have a different number for R if you changed those units. So those units are going to be very important to us. So the ideal gas law has a gas constant. So it's PV equals NR, the gas constant T. Or how my high school chemistry teacher called it, for whatever reason, PivNert. So that's one of the differences, is the gas constant. The second difference you may know is it uses all 4 of the variables. So we have in the same equation, we have pressure, volume, temperature, and the amount. So all 4 of them are present. Oops, sorry. So that's different because in the previous gas laws, we usually had 2 of the variables and the other 2 were held constant, or up to the combined gas law, which had 3 variables but still had that amount constant. So that's different. And then the third thing, in this gas law, there's no changing. You might think, what do I mean by no changing? And that means, what I'm trying to get at is there's no 1s and 2s. So this gas law isn't in particular of what we would say if we wanted to, if we could hold some things constant and say, oh, if I change the volume, what happens to the pressure? This gas law is more of an instant where we know 3 of the 4 conditions that are present for the gas. Now, the ideal gas law is a quite versatile gas law, and in this introductory class, we won't get to use it in all the different ways it can be used. If you take Chemistry 1, you'll get to use the ideal gas law a little bit more to its full capacity. But it is very versatile gas law. And the other thing, again, that's cool about these gas laws is because of how gases behave, we can use this for any gas or any mixture of gases. So that's kind of a neat thing. So why don't we go ahead and take a look at an ideal gas law problem. So in this problem, it says, let's just read through the problem. So it's asked us how many moles. So I think to myself, okay, I need N. Of carbon dioxide are contained in 9.55 liters. That's my volume. At 45 degrees Celsius. Well, that's my temperature. But before I even get going, I think to myself, okay, 45 degrees plus 273, because I know I can't use Celsius without and get the answer right. You have to be in Kelvin. And that's 318 Kelvin. And then I also have here the pressure. So when I look here, I say I have pressure, volume, temperature, and the amount. So this is a perfect reason to use the ideal gas law. So I say PV equals nRT. Now remember, something I need to check is my R is 0.0821, and it has liters, atmospheres, moles, Kelvin. And remember, I told you those units are going to be important. So when I look, the volume I was given was in, just a minute, I'm trying to get a little bit lighter color highlighter. Okay, sorry. The volume I was given is in liters, right there, and the R has liters, so that's okay. The temperature I calculated was in Kelvin, and this is in Kelvin, so that's okay. But I look here, and I was given torr, But the gas law has atmospheres. Okay, that is not okay. So before I even get going, I have to convert torr into atmospheres. So I remember that 1 atmosphere equals 760 torr. I actually give that to you. So I say 752 torr. I'm going to put 760 torr on the bottom, so my torrs cancel. And so my pressure in atmospheres, which I need to use, so that's 752 divided by 760, to 3 significant figures is 0.989 atmospheres. And then I'm okay, because now I have atmospheres and that matches. So one thing you might want to pay attention to when you're doing an ideal gas law problem is that the units you're plugging in match the units that are in R. Otherwise, again, it's a situation where you could do the math correctly, but get the wrong answer because your units are not matching. So let's plug in into the gas law. Okay, so pressure times volume. I'm going to change to a black pen. So 0.989 atmospheres times the volume, 9.55 liters, equals N, and I don't know N yet. That's what I'm solving for. And then 0.0821, that's all these units, times the temperature, which is 318 Kelvin. Now, if you're following your units, the Kelvin at this point cancel. So you might want to pause here and go ahead and do your math so you don't get confused by how I set it up. I'm going to go ahead and multiply these two sides. I get 0.082. Now I'm multiplying the other side. This is 26.1078, and it still has kind of crazy units because all I got rid of was Kelvin. And so now I need to solve for N, so I'm going to divide over. So N equals 9.44495 divided by 26. Now again, I wanted to show you, I know it's very exciting, but see, atoms cancel, liters cancel, and I'm left with moles, which is what my answer should be in. I always like it when it works out that way. 9.44495 divided by 26. And if I wasn't doing this video, I'd probably find a way where I didn't have to rewrite so much stuff, just because that's where I make my mistakes. And I get to 3 significant figures, 0.362 moles. So if you reread the question, it says how many moles of carbon dioxide are contained in 9.55 liters at 45 degrees at 752 torr, and the answer is 0.362 moles. The cool thing is, again, it doesn't matter that it's carbon dioxide. Any gas or mixture of gases at these particular conditions would have that same number of moles. Now, if the question asks for grams, remember, the ideal gas law is going to give me moles. So if I want to go from moles to grams, I've got to dig back. Moles to grams uses the molar mass. And then it would depend on carbon dioxide, because we get our molar mass by adding up the elements' masses from the periodic table. So if you want to see another ideal gas law problem worked, go back into the class lessons and you'll see that there's at least one more problem worked that you can give a shot, as well as in the cross practice worksheets.